Hello everyone. In this video, we'll be looking at the modeling and simulation of physical systems. Now, physical systems are systems that we deal with on a regular basis, and there's no way we want to actually design or develop a physical system without modeling and simulating what the performance of that physical system will be like when it's in operation. So modern simulation is very important to understanding the behavior of any physical system before they are being created in real life, because that will save us a lot of time in trying to reconstruct and reshape the physical system, since we can model them and simulate them in computer environments. So it minimizes the time and the cost of building a system that will not work and having to reconstruct and remodify it before it can work properly. All of the changes that we might want to make when we would have built them in real life could have been done while we are doing the modeling and simulation. So that is what we're going to be looking at in this video. So before we move on, we want to look at what mechatronic system or mechatronics itself is. So mechatronics is a methodology used for the optimal design of electromechanical products. So we all have heard of the word mechatronics, and what it is actually used for is to create electromechanical products that perform optimally. So mechatronics itself is a methodology by which we can create electromechanical products that will perform optimally in whatever area we deploy them to. But the methodology itself is the collection of practices, procedures, and rules used by those who work in a particular branch of knowledge or discipline. So, what we're saying about methodology is that a methodology is a standard way of doing things which is peculiar to a branch of knowledge or discipline. For instance, if we look at mechanical or electrical or maybe civil engineering, they have some kind of procedures by which they carry out their design. Those procedures, those practices, those rules that they follow, that is what is called methodology. So methodology is not universal, it is relative to different fields and disciplines. So we have different methodology in the area of probably electrical engineering, computer science, mechanical engineering. Several disciplines have their own peculiar methodologies. So mechatronics itself, or let me say, mechatronic system is a multidisciplinary system that includes various disciplines. Particularly, there are four key disciplines that you would find in a mechatronic system. Number one is the electrical, the mechanical, the computer, and information technology. Just like what we have here in this figure 2.11, showing the constituents of mechatronics. So on the right side, we have mechanical system, we have electrical system, and to the left, we have information system and computer system. For any mechatronic system to thrive or to be said to be a mechatronic system, it must include these four areas or discipline for it to perform optimally. Now, the word multidisciplinary system is not new. It has been in existence for so many years. Particularly, the most common one that we can relate with is the electromechanical system. And this is a system that uses a computer algorithm to modify the behavior of a mechanical system. For instance, you have a mechanical system. If we can take an example, we can look at something like the normal example of something that comes to mind is your normal electric motor. We all know an electric motor being an electromechanical system. It has the electrical part, equally has the mechanical part. But you can have such system whereby the speed of that, probably your AC motor or your DC motor, can be controlled such a way that the required speed is always obtained at all costs, at all times. And that will require a computer algorithm that would measure the speed of that electromechanical system while it is in operation, and try to do any correction in terms of voltage when the required speed at the output is different from what the sensor is measuring. So you can be having something like a PID controller in that sense that would compensate for any error with from the input to the actual output. So that's just an example of an electromechanical system that is being used in daily operations. So also you can use electronics to uh, modify such systems, basically to get some information from them while they are in operation, and that is where sensors comes in to transduce information between the computer science and the mechanical discipline, whereby as the electric motor is rotating, the sensor can actually measure the speed at the output shaft as against the set points. So the sensor measure the output speed at the output shaft, reports to the algorithm, which is basically the computer science aspect of the system, and the algorithm checks if the measured speed and the set points is equal. If it's not equal, then a computation algorithm such as your PID controller can now be used to, you know, compensate for the voltage that would make up for that difference in speed between your input and your output. So uh, those are areas where mechatronics has been used to improve the operations of normal electrical or mechanical systems in daily operations. So what we must also note is that the difference between a mechatronic system and the multidisciplinary system is not about their constituents. The mechatronic system and the multidisciplinary system, encompasses disciplines uh, more than one, you know. But where they differ is the manner in which these systems are designed. Multidisciplinary system used what we call the sequential design by discipline approach. What do we mean by design by discipline approach? We're saying that for a multidisciplinary system, the design is done in successions, whereby a certain discipline of the design completes their own uh, design, then pass the job onto the next discipline for the next discipline to carry out their own design. After their own completion, then they carry it on to the next discipline until the whole system is being completed. For instance, if a certain multidisciplinary system is to be designed, and that system will require electrical, mechanical, computer, disciplines to complete the design of that system. So what will happen is that the electrical discipline will complete their own design of that multidisciplinary system first. Then they pass it on to the mechanical. Then after mechanical is done with their own design, they pass it on to the computer discipline. That is what we refer to as sequential design by discipline approach, which is being used in the design of multidisciplinary system, which is not the case with mechatronic system, because in the case of mechatronic system, all the discipline, they carry out their design at the same time, and there's no need for having to carry on from one discipline to the other to the other. All the disciplines, they work together on the design of the system at the same time, and that is the advantage of the mechatronic system over the multidisciplinary system, because the approach of multidisciplinary system that uses the sequential design by discipline, what happens is that any constraint in a certain discipline on that design will be carried on to the next discipline, because the disciplines are not working together at the same time on the design. So discipline A complete their own aspect of the design, they pass it on to discipline B to complete their own aspect of the design, pass it on to discipline C, and on like that. So the constraint that would happen on the design based on the work of discipline A be passed on to discipline B. And that is what mechatronic system design eliminates, because such constraints are not passed on to the next discipline since all the disciplines are working together concurrently. So it eliminates such problems that design by discipline approach that it's bedeviled with in such instances. So I've already talked about this mechatronic constraints figure here, which we said mechatronic consists of mechanical system, electrical system, information system, and the computer systems. So we move on to the next subtopic, which is the operator notation and transfer functions. Now, why do we need this operator notation? Because we want to be building models of physical systems. It's best to find a way to easily represent these systems so that we don't have a much complex mathematical models on our hands. So that is why this operator notation and transfer function has been introduced. So I have here, I said, for ease in writing linear long parameter differential equations, the D operator is introduced. So any linear differential equation can be converted to operator form by simply substituting the operations using differential or integration with the appropriate operator. So if we look at this table, which is our table 2.2.1, sorry. So we have the type of the system, which are both continuous systems, because these are systems that their state changes with time. So these are continuous systems. So we'll be modeling continuous systems in this work. Then operations can either be differential or integration. And the D operator replacing a differential equation. Now we know what a differential equation looks like. Let me just open my whiteboard here. We know that whenever we have your, whatever it is, maybe your d dt in this form, you know that this is a first order differentiation. Now in this bracket, you can have anything. You can have probably x here, all right, which means dx dt. So that means we are differentiating x with respect to time, or it can be your dy, maybe dy dt, you know. That means you are differentiating your, you are differentiating your y with respect to time, you know, or it can even be current. It can be differentiating current with respect to time. That'll be your di. That'll be your di dt. So anything can be in this bracket. So once you have your d, this is just a bracket, and the t, because we are differentiating with respect to time, this by itself is a first order differential equation, you know, and the D operator can be used to replace all of this by just saying that your d dt, you know, equals your capital D. This D here, this capital D here is your operator notation in this case. So this is the operator. Differentiation is operator here, and the notation is this capital letter D in this case. For differentiation, for integration, for integration, your operator notation will just be the inverse of your differentiation, which is just saying if you are having differential of something like this, you have a differential of a certain whatever variable that is with respect to time from t naught. Sorry, let me just erase this. From t naught to t, which means you are differentiating from t, whatever start point of t is, to the maximum value of time, because we are dealing with continuous systems. You know, whatever variable we are differentiating with respect to time, yeah, we can replace all of this with the notation of 1 over d. So we are saying that for differentiation, your 1 over d is equivalent to this differentiation you have on this right side. And for your this is integration. So for your differentiation, you're saying that your capital letter D is equivalent to this first order differentiation. So for differentiation, capital letter D. For integration, 1 over capital letter D. So this is the operator notation, for integration, and this is the operator notation for differentiation. So that is what we'll be using to replace these operations in our mathematical models. All right, so before I go on to some complicated mathematical models, let me just show you what a simple mathematical model is. Let's assume that we have a circle. I want to know the circumference of this circle. We know that the circumference of a circle equals to 2 pi r, you understand, which means the radius of the circle itself and pi, which is 22 over 7, like we know that constant, and the radius then multiply by the constant 2, you understand. So this is the, let me just clean that off. So this 2 pi r is the mathematical model that we can use to develop the circumference of a cycle. So however big we want the circumference of that cycle to be, all we need to be changing is the radius, So once we get the right radius that gives us the right circumference that we want, then we know that that's the radius that the circle will be, in real life. For instance, let me say I want to have a dining table, and the dining table is circular in shape. Let me just take that as a circle. But I want to know what should be the size of this dining table. All I need to do is, okay, what is the circumference that I want? Oh, okay, I want circumference to be, let's say I want circumference to be 40. I want circumference to be 40. Let me say probably 40 mm. I'm just saying. And so that's the circumference that I want. So I know that will be 40 equals to 2 pi r. So all I need to do is to find the radius that will give me this 40. So that will just be my radius equals 40 divided by 2 pi. So from here, I will get a radius that will give me this 40 as a circumference. So that is just the basics of mathematical models. But in this course, we are looking at the mathematical models of continuous systems that their state changes with time. And we are going to be using the operator notation to, represent the differential and the integration in such equations. So let me just rub all of this. And if you go back to that same table 2.2.1, we have this model, which is your let me increase the font here, which is your x double prime. Let me just come here to write that. So you have your x double prime. That means that has been differentiated twice, and because we are dealing with time varying systems, so that would be with respect to t. So minus 3 x prime, that means differentiated once, also with respect to time, because we are dealing with continuous systems, plus x of t equals r single prime of t minus 1. Let me just rub this so that we don't mix it up with it. Minus 1. So if I want to use the operator notation to rewrite this equation, all I'll be needing is to replace this, since this is differentiation. So I know that I'll be using the d operator in this case. If it's integration, I'll be using the 1 over d operator. So I know that first order differentiation is d. So once the second order, that will be d squared. If it's third order, that will be d cubed. So this will be d squared x t. Now this squared xt, because my d is just my d dt, right? So my d squared is this, is d squared empty bracket d squared dt squared in this case. That's my d squared. So if I return that, I'll still be needing my x into this space. So that's why I have it d squared xt, showing that we're differentiating with respect to time, minus 3, that will be 3d, that will be 3d xt, then plus xt, because it has not been differentiated at all, so it's just normal xt there. But r here has been differentiated once, so that will be d r t minus 1. So what I've done here is to rewrite this equation using the operator notation form here, replacing where I have my differentials or differentiations with the d operator. If it's an integration problem, I'll be replacing where I have my integration with the d operator. If we look at the next model in that same differentiation row, we have the x dot saying x have been differentiated once, x of t plus x of t minus the integration of x in bracket this variable here is the time, and t plus r of t equals 0. So I just want to rewrite this using the operator notation. We know that my first differential is my d. So that will be dx, that will be dx, that will be dx of t, dx of t plus xt, because xt here was not differentiated at all, so we can't replace it with the operator notation. But here we have a differentiation, and we know that this first integral is represented by 1 over d in the operator notation. So that will be 1 over d, x t, because this variable here is x and is differentiated with respect to time, x of t, plus r here was not differentiated at all, so that will be r of t. So r of t equals 0. So what we have done here is to replace this equation using the operator notation form here. So that is just what we have done, which is what we have in this table. So what we're going to be working with is actually to rewrite these equations, either differential integration using the Laplace form. And we all know that in the Laplace, we have systems that are time varying system. So we also need to know that the cause effect relationship for any system, can be approximated by a linear or ordinary differential equation. For instance, if we consider this second order differential equation, second order because the y here was differentiated twice, and that's the highest order differentiation in this equation. That makes this equation a second order. So this y is in second order, the y here is in first order, while this one was not differentiated at all. But this r here also is in first order, while this r here was not differentiated at all. So having y here differentiated twice with this double dot, that makes this equation a second order differential equation. And also we are told that the input in this equation is r, while the output is y. And we can see from this equation we only have two variables, y and r. And we have been told that the r is our input and the y is our output. So that makes this system, right, this physical system, having this mathematical model, a single input, single output system, which we refer to as your SISO system. The system having only one input and one output. So to obtain a transfer function itself is the ratio, transfer function, let me call that capital TF, is the ratio of your output, outputs of a system to inputs of that system. That is what is called transfer function of a system. So for the one we are talking about, we're told that our y with respect to time is our input, so our output, while r with respect to time is our input. So the TF is ratio of your output to input, your transfer function of any system. So for you to obtain the transfer function of any system, there are three basic steps that you must go through. So the first step is to rewrite that system equation using the operator notation. And if we go back here, we can see that we have y, double dot with respect to time, and we have minus 2 y single dot with respect to time as well, then minus 7, plus 7 y with respect to time, equals r single dot differentiated once respect to time minus 6 r of t. So to rewrite this using the operator notation, by now we know that this double dot means second order and single d is for first order. So d squared will be for second order using the operator notation. So that will be d squared y of t. D squared y of t. Y of t. And minus 2d y of t as well. Then plus 7y of t, because that y here has not been differentiated at all, equals d, because r here was differentiated once, r of t minus 6RT. So we have been able to rewrite this equation using the operator notation. Then after then, what we need to do is to collect the like terms, or just say factorize by both the output and the input variable. So if you factorize and make sure your output is on the left of your equality sign, so if you factorize by y here, we're going to have d squared minus 2d plus 7. Let me just add the time to this. So that'll be y of t. So factorize by y of t equals, factorize here by r of t, because r of t is my input. That would be d minus 6. So the tf, which is the transfer function, is y of t over r of t. So if we cross multiply here, so that will be d minus 6 divided by d squared minus 2d plus 7. So this is the transfer function of this second order differential equation that we are given. The first thing we did here is to rewrite the equation using operator notation. The second thing is to collect the like terms, having our output to the left of the equality sign and the our input to the right of the equality sign. Y is our output, R is our input. Collect, factorize using R, factorize using Y, and the TF transfer function is ratio of output over input, and this is what we have here. So that is what is called a transfer function. I've just tried to explain these 3 steps here. Rewrite the equation using the operator notation, which we did. Step 2, collect and factor all output terms on the left side and input on the right. Then 3 is to obtain transfer function by way of the ratio of output over the input. So that is the steps required when you want to get transfer function of a certain system. So the next subtopic we'll be looking at is your block diagram, manipulation, and simulation. So simulation itself is the process of solving a block diagram model on a computer. So that is what simulation is in this context: solving a block diagram model on a computer. So, but generally, simulation is the process of solving any model. Simulation is the process of solving any model. But in the context of this course, simulation is being referred to as the process of solving a block diagram model on a computer. So, block diagram is the common term used when we are talking about models in this case. So when I mean block diagram, I mean the mathematical model of a certain system. So we can build block diagrams using visual programming environments. There are several visual programming environments available today. For instance, you have your Simulink that comes with MATLAB. Simulink is an application in MATLAB that is being used for visual programming when you'll be using block diagrams to model any system. So we have other examples of such systems in existence. You have your Finzim, Also, we have the lab view. We have the matrix system. There are several uh, types of such visual program system. There's also the Easy 5, that's the Boeing. So there are several of them. Whichever one you are comfortable with would be the one that you might be using, or whichever one you know can serve your discipline appropriately. For instance, for me, I use MATLAB, and I use Simulink. This is Simulink environment in MATLAB, so I can from here model any system using any of the libraries. For instance, let me say I just want to model the circumference of a circle that we talked about. So all I would know is the circumference. I just want to obtain the radius, and from the model that we did the other time, we saw that the radius would be the output of the circumference divided by 2 times pi. So what I'll just do is to form a mathematical model that will be giving me the radius of a certain circumference of a circle. So if I call this the radius, if I call this the let me just annotate this first. Call this the circumference of the circle, which I'm going to input myself, and I'll pass the signal into the constant of 2, where I will divide by I'll be dividing by 2. I'm not changing the time step just yet. Where I'll be divided by 2 I'll be divided by 2 over the product of 2 and pi. So let me just have a display block where I will display my output, which will be the radius in this case. So let me just call this display block. Let me call it my radius. The radius. So what I want to have here is my circumference, my constant, which is the 2. This one will be the constant in this case, which is normally 2, because we know the circumference of a cycle is 2 pi r. So I will have 2 here in this constant block. Then this constant blocks, that will be 3 points. Sorry, let me just recall. 22 divided by 7 is. So let me just connect all the blocks. You know, we have 2, which is the constant here. This is our pi divided by 7. So I need to multiply these 2 using this products block here. And the output of these products would come into this division input channel. And the circumference here will now come here. So what that means is that the circumference here divided by 2 times pi. So the product here, I'm putting it into this display block here. And if you just put any circumference here, let me say I put 4 there, and I run this simulation. So the value I have here is the radius of that cycle. If you try with a calculator to see if you're correct or otherwise, you will see here that 22 divided by 7, multiply by 2. We take the inverse of that, then times it by 4. You are going to have 0.6363 6, which is the same as 0.6364. So it's correct. What I just did was to do, you have the circumference of a circle as C equals to pi r And since I'll be knowing my circumference when I'm doing any design, so it's my radius that I will look for. So that will be radius equals circumference divided by 2 pi. So this mathematical model here is what I've represented using Simulink in this case. Simulink is a visual programming environment, which is an application in MATLAB. So all these are your blocks. They're called your blocks. And all these lines are referred to as your signal lines. So signal lines, on this signal line, the value of 4 is what is on this signal line. On this line is value of 2. On this line it is 3.1428. And on this line is the product of these two that is on this line. So if you want to find out, you can put a display block, on this line and attach it to this line. And if I run this simulation, you see that whatever value I have here is the product of these two, because 2 times 3 will be 6, 2 times 1 will be 2, 2 times 4 will be 8. So we can see that the product of this is what is running on this line. So that's what your signal lines are, just to show us by way of example. Now, block diagrams itself, introduction to block diagrams. For any block diagram model that you have, it consists of 2 fundamental objects, the signal wire and the blocks. If we go to the MATLAB diagram that I show in Simulink here, the blocks, these are the blocks. These are the blocks. It consists of the blocks and the signal wire. These are the signal wires. So any block diagram will consist of 2 objects, the block or the blocks, and the signal wires. Those are 2 objects you find in any block diagram environment that you might have created before you can say you have done a block diagram. Now, the function of the signal wire is to transmit a signal or value from the origination point, usually a block, to a termination point. If we go back again to that MATLAB Simulink, you can see the function of this signal wire is to transfer the value of 4 from this block to this division, and also this same signal wire carries 2 from this block into this. Also, this signal wire here carries the value of this 3.1.428 into this block, and this signal wire here carries the product of these 2 as the output from here into this division input of this division block. So a block is a processing element which operates on input signals and parameters to produce output signal. So a block by itself is a processing element. It operates on input signal and parameters, whatever parameters that there is, and produce the output signal. If you look at this product block has 2 inputs from this constant block of 2 and this constant block of 3.1428. So what happens in this block is the multiplication of these 2 signals, and it gives an output of their product, which is what we are seeing on this display block here. The product of this and this is what this block will compute, and the output will be that same signal into this destination. So the major blocks that does these operations are your summing junction, the gain, and the integrator. Let me just show you in the library of Simulink. Let me show you the gain block. The gain block. This is the gain block. So you have the gain block. This is what your gain block looks like. And also you have the integrator. which is this block, is what is referred to as the integrator. 1 over S, same thing as your 1 over D. Because in Laplace, the D operator is same thing as your S operator. So 1 over S is same thing as your 1 over D. And the sum or summing junction, which is just what we would see now. So this is your sum. This is the sum block. You have two inputs, one input from here, one input from here, and gives one output. Also for your integrator, one input from here and one output. For your gain block, one input and one output from the other end. That is what the basic blocks that you have in your visual programming environments. So an example showing the three blocks is shown in your figure 3.2, 2.3.1, where you have your sum or summing junction, you have your gain, and you have your integrator. Now, every integrator has what we call the initial condition, which is the Y naught here as initial condition. So your Y capital here is the output, while your R is your input. This also is a system on its own, and it's a single input, single output system, because only R is the input here and Y here is the output. When your Y naught is the initial condition for this integrator block. So this is just your integration block by itself. You can have it in this form to show your initial condition, or you can use this method also to show your initial condition on your integrator block. But this is a convention that we're going to be using in this class. So that takes us to what we call the block diagram manipulation. So there are several ways by which we can manipulate block diagrams. Now, why do we manipulate block diagrams? We manipulate them because we want to reduce their size. Because when you see block diagrams, sometimes they might be just too cumbersome. So it's best to find a way to minimize or to reduce your block diagram so that they can be readable to anyone that wants to use them. Because block diagrams are not created in any standard form. So because there's no standard form by which you can say, oh, this block diagram must be created using this standard form. So based on that, if I give a question to several students, different students will come up with their own designs of block diagram or block diagrams. So one way by which we can, modify them is to reduce them using the block diagram manipulation methods, and for efficiency and for readability, it's always good to minimize these block diagrams. So I'll just be showing you these methods. The first type is when you have block diagram where you have the blocks in series or in parallel. When you have the blocks in series or in parallel, if you have two or more blocks, in successions in this way, whereby the same input is flowing through these blocks. We can see here X is the input into A goes into B goes into C. This makes this block a series arrangement. And based on that, instead of using these three separate blocks, we can have a single block whereby we have the product of A, B, and C in that single block. This is a way by which we reduce a series connection of blocks in this way. When you have one input going into a certain block, and the output of that block goes into another block. The output of this block goes into this other block. Then these blocks in these successions are in series, and therefore we can minimize them by using a single block, while we have the product of these three blocks in that single block. That is for series manipulation. Then we have for the parallel manipulation, when we have blocks in parallel in this form. Now, for us to be sure that they are in parallel, we must be cautious of the fact that it must be the same input signal that goes into these three blocks, or into these blocks that are in parallel. Blocks can align in this stack, in this vertical stack, you understand, but they are not in parallel because it's not the same signal that is going into them. But in this case, we have A, B, and C stacked in this vertical manner, and the same signal of X here is going into A, is going into B, is going into C. That is what makes these three blocks parallel. If there is a case whereby input X is going into A, input Y is going into C, input Z is going into this other block down here, and that makes them not parallel because it's not the same input signal that is going into the blocks. But when we have the same input going into these blocks, then we can say they are in parallel, and we can replace them with a single block where we have the summation of these blocks in that single block. That is for parallel manipulation. Then we have what we refer to as the pick-off point. Now, manipulation based on pick-off points. Now, pick-off point by itself is when you have a certain signal wire, that is being connected to an existing signal wire, which means the same signal flowing in wire A is flowing into wire B, which means wire B now is having its own pick-off points from wire A. Let me show you that in MATLAB here. If we look at this model that we built the other time, the signal going into this display block, right, is picked from this wire. Let's say this is wire A now. This is wire B, right? This point here is the pick-off point, which means this signal going into this wire is picked up from an existing wire, right? That is what we call a pick-off point. This is a pick-off point, right? This is a pick-off point because this wire is connected to this existing wire. I can have several pick-off points on the same wire. I can have another pick-off point here. This pick-off point here is from this same wire. The same signal that is flowing into this display block is the same signal that will flow into this integrator block here. I can pick the same signal again into this gain block. All these points are pick-off points from this single wire. And when you have a pick-off point like that, that pick-off point, what will flow into that pick-off point, into this wire, is the same signal that is flowing on this wire, which is this same 6.286, is what is flowing into this display block, is flowing into this gain block, is flowing into this integrator block. So all these points, point 1, 2, 3, if you call it so, are pick-off points on this signal wire alone. So that is what we call a pick-off point. When you have pick-off points are wire origination points located on a wire as opposed to a block output. Let me show you what a block output is. For instance, this wire here is from the output of this block. It's not from a pick-off point, right? Every block, most blocks have input and output terminals. For instance, this sum block here, this is input 1, input 2, this is the output, right? So the same thing for this product block, input 1, input 2, output. Division block, input 1, input 2, output. So the difference between having a pickup point and a normal signal wire from an output is that the pickup point will be on a wire, not from the output of a block. So that is the understanding of pickup points and regular output. But for pickup points, the signal on the wire that pickup point is picked from is the same signal that will flow in that wire. So if you look at these blocks in parallel, you can see that X here is a signal flowing into B, and the pickup point here goes to A, the pickup point here goes to C. That makes these blocks in parallel because the same signal, which is X, will flow into all of these blocks. So that is what we call a pickup point. So for pickup point manipulation, we can have what we call the downstream manipulation or the upstream manipulation. What do we mean by downstreams? When we shift downstream over a block, when we move a pickup point downstream over a block. So if we look at this diagram 2.35 here, this point here is a pickup point that goes into this block C, right? And the signal flowing there is signal W. X flows into A, W flows into B. It's just letters that represent whatever signal that is flowing on that line. And Y is the output flowing out from B. And this W that is flowing from A to B is the signal on this line and is being picked off into C, which means W flows into C as well to give Z here. Now, if we move this pickup point, this point here, move it over this block B, that's downstream. If you move it over this block B, downstream, what will happen is that the inverse of the block we move this pickup point over will appear on the feedback part of that pickup point. We moved this pickup point over B. We move it over B to bring it to this point. The inverse of the block we moved it over will be on the feedback part of that pickup point. That's why we have 1 over B here, because we move this pickup point over this block, and the inverse of the block we move this pickup point over will appear on the feedback part of that pickup point. That's why we now have 1 over B into C. This is the same thing as this. If you want to check, you can check that using the mathematical model that brought up this block, as against its downstream pickup point movements equivalent. If we want to do that, if we go to let me just split my screen so that you can see what I'm doing. This is the block. Let's show the mathematical model of the first block of this block. That's X into A, right? A into signal W into B, then that gives your C. Or okay, let's even leave it now. Let's still understand the context before we now go into the mathematics that brought them about. So for upstream movements of a pickup point is that you move a pickup point, backward. You move it backward over a block. So when you move it backward over a block, the block that you moved it over, that block will appear on the feedback part of that pickup point. Unlike the downstream, when we move in this manner, we move to the right for downstream, you move to the left for upstream. So move to the right for downstream. The inverse of the block you move it over will appear on the feedback part of that pickoff point. But for upstream, when we move to the right, when we move to the left, so we move from here to here, move the pickoff point here from this point to this point. When we do that, that same block that we moved it over will appear on the feedback part of that pickoff point. So this is what we have. We move it from here over B, and B appears on the feedback part of that pickoff point. So that is for the upstream and downstream movement of pickoff points. We have talked about series and parallel. We have talked about upstream and downstream movements. Now we want to go to moving block or blocks itself over the summing junction, which means you have a block and you move that block over the summing junction. In this case, you need to work with the mathematical model of the blocks. In the same manner, you can either move the block downstream over the summing junction or upstream over the summing junction. Let's look at figure 2.37 and 2.38. No, this is 2.37. This is 2.38. Now we have this summing junction. These are summing junctions. So if we move a block, downstream, which means, for instance, this K now, if I decide to move it downstream, which means I move it to the right of this summation block, that's downstream. If I move it, to the left, in this case, downstream. If I move it to the right, in this case, upstream. So, but for me to know that the diagram I'll be given after the movement of the block or blocks is still equivalent to the initial one, I must first of all know the mathematical model of the initial block, right? And compare it with the new block I'll be having, block diagram I'll be having after I have moved the block over the summing junction, to know if they are equivalent or not. For instance, this model here, the mathematical model of this block diagram here is this. Y is the output, so that will be, so x minus z goes into k. So that will be y equals w minus k into x minus z. This is this mathematical model of this block. Y is my output, y to the left of my equality sign. And from this input axis, I have z flowing on this line, going into the summing junction, negative terminal, x flowing on this line, going into positive end of this summation junction. So that will be x minus z will be the output on this signal wire here, going into k. So that means k into x minus z. And that's all of this. K into x minus z is the signal flowing on this line, going into negative terminal of this summation block. And W is coming here to the positive end here. So that will be W minus K into X minus Z equals Y. So that's the model that brought this mathematical, this is the mathematical model for this block diagram here. And so now say I want to move K downstream. I want to move K downstream, move it to the left of the equality sign. Move it over this summing junction. Move this block K over this summing junction. Downstream, that's to the left. So, the block I'll be getting, I must ensure that the mathematical model of this block is the same as this one. And how do I do that? If I move this block to the left, so my question will be, if I move to the left, is it going to be on this signal line alone or on both? And if it's going to be here or here, in what form? Is it going to be as K or as 1 over K? So, this is the movement over the summing junction. If, for instance, I have moved it just over the summing junction and I put it on this X line alone, let's see the model that we're going to have. That will be XK. Let's assume this K was not here. I didn't know I was to put it here. That will be XK Z minus. That will be XK minus Z will be the signal on this line. So I'll be having XK or KX, whichever one is convenient, minus Z, will be the signal on this line, right? Plus W. So, and since the signal here is coming into the negative terminal here, that will be all of this in brackets minus W equals Y. Now I wrote this assuming that I only move this block over this summing junction and I put it on this line alone. So I will now check the mathematical model to the original one, which is this original mathematical model. This and this are not the same because the K here is multiplying both X and Z. But if when I move this block over this summing junction, I didn't put it on these two lines, I went on to put it on either one of the two. This is what I'll be getting as mathematical model. And if I look at it, it's not the same, right? Which means the only thing that will happen is that I still need the same K on the line of this Z. So that I'll be having something like Y equals W minus KX minus KZ. So I can have the factorized version of K into X minus Z minus Z W equals Y. So that is why I have, when I move this K, moving it to the left, it must appear on both the signal of X and Z. That is the only way this mathematical model here that I will get from this block diagram will be equivalent to this one. If not, I'll be getting something like this, which is not what I want. If I go on to move the K to the left and I put it on either this line or this line alone, and I didn't put it on the two, I'll be getting something like this, which will not be equal to the original model. Let me rub this and show you this next diagram. So this is the next one. I have this block diagram already. And I want to move K downstream, which means I'll be moving it to the left of an equality sign, moving a block over a summing junction. So I want to move it downstream, move it to the left of the summing junction. So that means I have to move this K over this summing junction, over this one. So what is going to happen? So how would that come to be? So let's first of all write the mathematical model that brought about this very block diagram. That will be KX will be on this line, W will be on this line. So that will be W minus KX on this line, right? W minus KX plus ZK equals Y. So that will be Y equals KX W minus KX, because W minus KX is here, W minus KX plus ZK. So that will be or kz, whichever one you want to call it, kz plus all of this. So w here, kx on this line. So w minus kx comes to this line. Zk comes to this line. So this plus this. So that will be w minus kx plus zk equals y. So this is the model that brought this block diagram. So to now move this k downstream, I move it downstream, right? What will be the equivalent block? What is it going to look like? So just simple. Since what I have is kz plus w minus kx, so I'll just be saying my y, once I move it over the summing junction, so that will be is the same as this block. That's kz plus kx minus w itself here. So that will be w. That will be w. That will be w. Plus kz minus kx. This is the same thing as kz plus w minus kx. So this block here is the same as this. Having moved this k here downstream, we can also have an upstream movement of a block over a summing junction. Over a summing junction, of a block over a summing junction. So this is upstream movement. Upstream. So that means I want to move the block from the left to the right of a summing junction. That is upstream movement of a block over a summing junction. So before you do the movement, first of all, check the mathematical model of the original block itself. So what's the model of this block? So this is z, kx on this line. So kx minus z is on this line. So I'll be writing the mathematical model now. So I just come here, that will be my, so I'll be having kx minus z. So kx minus z come out here. So w plus that one will give you the y. So that will be w plus kx minus z, equals y. So this is the model that brought this to be. W here plus whatever is coming out here, and that is kx here, z here. So kx minus z. So w minus kx minus z. So that's the model here. So to now move this block upstream, to move it upstream, so that means I want to move it upstream over the summing junction. Move it to the right of this. So this k will now come here. So what will happen is once this k comes here, how do I ensure that the model is still the same? If I move this k from here and I move it here, and I don't put the k on any of these lines again, what I'll be having is y equals w, plus k into x minus z, which is the same thing as saying kx minus kz minus kz equals y. Let's assume I just move this k to this right side of this summation block without putting it again on any of this line. That's what I'm going to be having. And if I look at this model that is the mathematical model for this block diagram, and when I move this k over this block, just move it over here, this is what I'm going to be having, because the x and z will be x minus z will now run into k here. You understand? And that will be giving me k into x minus z. That will be kx minus kz, which is not this mathematical model. So the only way that could happen is if I have z over k, where I have y equals w plus k into x minus z over k. So that when I multiply this, that will be k, x, and k will cancel k, that will be z, which will return this model for me. So that means on the signal line of z, I must have 1 over k there. So that's why when I move this k over this block, I must put 1 over k here to ensure that I have z over k coming to this terminal. So that will be x minus z over k to get to this point. Now runs into this k and comes out here. So that is what I have, k into x minus z over k here, plus w to give me y. That's the only way this and this is now equal. You understand? But if I went the route of just moving the block, the k over the sum junction, if I just move it over the sum junction, right, without putting it on any of this line again, this is the model I will be getting, which is not the same as this. So I have to find a way to make it the same. The only way that it can be the same is if I have z over k. So that when I open these brackets, I will have kx minus z, just like I have here. So that means on the signal line of z, I must put 1 over k there. That is why you have this 1 over k on this very line. So this k here also, I can still move it upstream. I can move it upstream here. If I move it upstream here, so I know the model now that brought this about, which is this, right? So if I move this k also upstream here, what's going to happen? So I'll be having all of this, run into the k that is here before the y. So if I just move this k here, if I move this k here, and I didn't repeat it again on any of the signal lines, this is what I'll be having. That'll be y into k into w plus x minus z over k. This is what I'm going to be having. If I move this k, I move it here, I move it from here, here, and I didn't repeat it on any of these blocks. When I move it upstream, so I move it downstream to the right. Now what we did here is upstream movements. What we are doing here is downstream movements. So if I look at this, it's not the same as this, because if I open this bracket, that will be kw plus kx minus z. It's not the same as this, because the w here didn't have k as a product here. So what will happen is that on the line of w, I need to have put 1 over k there. So that I'll be having here w over k plus x minus z over k. That's the only way when I multiply now. That will be kw divided by k. That will be w plus kx minus z. So that's what will give me this original equation back. So that's why when I move this k over this downstream, I need to return 1 over k on this very line of W, so that the model of this will be the same thing as model of this, and will be the same thing as the model of this. So that's downstream movement. Downstream movement is movement to the right, upstream is movement to the left. So for the manipulation, we have talked about series and parallel. I talked about the series and parallel movement. Series, parallel. I talked about movement over a movement of a pick-off point, either downstream or upstream over a block. And we have talked about you're moving a block itself or blocks through the summing junction. Either you are moving the block through the summing junction upstream or downstream. But when you're talking about upstream or downstream, you're moving a pick-off point over a block downstream, or you're moving it backward, upstream over a block. That is movement of pick-off points, downstream or upstream. Movement of blocks over summing junction, downstream or upstream. Then we have the parallel and series manipulation. So those are 3 manipulations that we have. So let me just rub this and we move on. So this will be the end of this first part of this class. The next class we'll be looking at the basic feedback system and how we can use these manipulations that we talked about to minimize our blocks. Thank you.